Good day, everyone. We are BS Electronics Engineering students from Bicol State College of Applied Sciences and Technology. In this presentation, we will be focusing on 16-phase shift keying modulation, a higher-order digital modulation technique widely used in modern communication systems. In this topic, we will discuss the introduction to digital communication, basics of 16-phase shift keying, its signal representation, performance analysis, applications, simulation using MATLAB and MATLAB Simulink, and lastly, the conclusion. In electronic communication systems, digital communication is a combination of two different words, digital and communication. Here, the term digital refers to the discrete time version representations of electronic signals or information signals, while the term communication refers to the process of exchanging information between two or more devices or entities. Therefore, the term digital communication refers to the process of exchanging information digitally. To transmit data, we use modulation. In this presentation, we will only be focusing on the digital side. Digital modulation is a fundamental process in modern communication systems, encoding digital information into amplitude, phase, or frequency of carrier signals to enable efficient and robust data transmission. Hence, traditional electronic communication systems that use conventional analog modulation such as amplitude modulation, frequency modulation, and phase modulation are rapidly being replaced with more modern digital modulation systems that offer several outstanding advantages over traditional analog systems. Now, the question is, how do we transmit a stream of digital bits over a communication channel? A digital bit stream consists of only zeros and ones, but these baseband digital signals cannot be transmitted efficiently over long distances or wireless media. To solve this problem, we use a process called digital modulation. One common digital modulation method is shift keying. In shift keying, the carrier wave does not vary continuously like in analog modulation. Instead, one parameter of the carrier, either amplitude, frequency, or phase, is shifted between discrete values. Each discrete shift corresponds to a digital value, allowing the carrier to represent binary data. Initially, binary data can be transmitted using two discrete signal states, representing logic 0 and logic 1. However, transmitting only one bit per symbols limit the data rate. To increase the transmission efficiency, multiple bits are grouped together and transmitted as a single symbol. This concept leads to M-ary shift keying, where the carrier can assume different discrete states. Each symbol now represents more than one bit, allowing higher data rates without increasing bandwidth. This principle forms the basis of the advanced modulation schemes such as M-ary PSK, including 16 PSK. Moving forward, now we have the types of digital modulation techniques. Digital modulation techniques are classified according to which parameter of the carrier signal is varied in order to represent digital information. Based on this principle, there are three main types of digital modulation techniques. The first is amplitude shift keying, or ASK. In ASK, the amplitude of the carrier signal is varied to represent binary data, while the frequency and the phase remain constant. Typically, a higher amplitude represents binary 1, while a lower or 0 amplitude represents binary 0. Although ASK is simple to implement, it is highly sensitive to noise, which limits its use in practical communication systems. The second technique is frequency shift keying, or FSK. In FSK, the frequency of the carrier signal is shifted based on the digital input. Two different frequencies, usually denoted as f of 1 and f of 2, are used to represent binary 1 and binary 0. Because information is encoded in frequency rather than amplitude, FSK offers better noise immunity than ASK, though it generally requires a wider bandwidth. The third technique is phase shift keying, or PSK. In PSK, digital data is represented by changing the phase of the carrier signal. While its amplitude and frequency remains constant, the simplest form of PSK is binary phase shift keying, or BPSK, which uses only two phase states separated by 180 degrees to represent binary 1 and binary 0. PSK provides better noise performance and power efficiency compared to ASK and FSK, making it widely used in modern digital communication systems. Next, we have the basics of 16 phase shift keying. 16 phase shift keying, or 16 PSK, is a higher order digital modulation scheme that belongs to M-ary phase shift keying family, where the numbers of distinct signal states, or M, is equal to 16. In this modulation technique, digital information is transmitted by shifting the phase of the carrier signal among 16 discrete phase values. The amplitude of the carrier remains constant, and only one phase is varied to represent different symbols. Because the signal has a constant amplitude, 16 PSK is less sensitive to amplitude variations caused by noise and is well suited for use with power-efficient and non-linear amplifiers. In M-ary modulation schemes, each transmitted symbol represents a group of bits rather than a single bit. The number of bits carried by each symbol is given by the relationships. For 16 PSK, we have 4 bits per symbol of logarithmic 16 with a base 2. This means that each symbol in 16 PSK represents 4 bits of digital information. By transmitting multiple bits per symbol, 16 PSK achieves a higher data rates and improves spectral efficiency compared to lower order PSK schemes such as BPSK and QPSK. Now we have the phase separation in 16 PSK. In 16 phase shift keying, the complete 360 degrees phase circle is divided equally into 16 discrete phase segments. As a result, the angular separation between adjacent symbol is given by the change in delta is equals to 360 over 16 or is equals to 22.25 degrees. These relatively small phase separations allow a great number of symbols to be transmitted within the same bandwidth, leading to high spectral efficiency. By encoding more bits per symbol, 16 PSK achieves higher data rates without increasing the symbol rate. However, the close spacing between the phase states means that the receiver must distinguish very small phase differences. Noise, interference, and phase distortion can easily cause the received signal to be misinterpreted as a neighboring symbol. 16 PSK is more susceptible to noise than lower order PSK schemes such as BPSK and QPSK, and therefore requires a higher signal-to-noise ratio or SNR for reliable operation. For the symbol representation of 16 phase shift keying, the truth table defines the mapping between 4-bit binary input to symbols and the corresponding carrier phase angles used in 16 PSK modulation. Since 16 PSK has 16 possible symbols, each unique 4-bit combination is assigned by a distinct phase separated by 22.5 degrees. Phase values listed in the table are centered between in the in-phase or cosine and quadrature sine axes rather than aligned exactly on them. This offset improves symmetry in the constellation and simplifies phase detection at the receiver. The bit codes are arranged using gray coding, meaning that adjacent phase states differ only by 1 bit. This minimizes the number of bit errors when noise causes the received symbol to be detected as a neighboring phase, thereby improving the overall bit error or BER performance of the system. During the transmission, the modulator consults this truth table convert each incoming 4-bit group into its corresponding phase shift. At the receiver, the detected phase shift is compared against the same table to recover the original digital data. Now we have the symbol representation of the 16 PSK, the constellation diagram. This diagram provides a graphical representation of the 16 PSK signal in the in-phase or I, in the quadrature or the Q plane. Each point at the diagram corresponds to a unique 4-bit symbol, and represents a specific phase of the transmitted carrier signal. The angular position of each encodes the digital information, while the distance from the origin remains constant, indicating a constant signal amplitude for all symbols. The constellation points are uniformly spaced around a circle, with an angular separation of 22.5 degrees, reflecting the equal phase spacing used in 16 PSK. This circular arrangement highlights that information is carried solely in the phase of the signal, not in its amplitude. Encoding is also applied to the constellation such that adjacent symbols differ only by 1 bit. This is an important design feature because noise and phase distortion may cause the received signal to be detected as a neighboring symbol. With gray coding, such symbol decision errors results in only single bit error, significantly reducing the bit error rate or the BER and improving the reliability of the communication.